indeterminate forms and the L'Hopital rule. In this video, I will discuss the indeterminate forms, but we will only focus on the power forms. 0 to the 0, infinity to the 0, 1 to the infinity. Of course, we remember that each of the symbol, like 0 and infinity and 1, representing a function that is approaching these values. Okay, that means indeterminate power forms are function, yeah, we have a limit with that form, function taken to the power of another function, and with the certain condition, one function goes to 0 and another goes to 0. That's the form 0 to the power of 0. We don't know what it is right away. We cannot assume is possibly 1, possibly 0. We don't know. Could be anything, is indeterminate form. And then we have another one. One function is approaching infinity, another function is approaching 0, and respectively the same. One function goes to the 1, one function goes to the infinity, could be positive or negative. Okay? And the other like variation of this infinity, zeros and ones are not the indeterminate, only this. Like for instance, when we will take infinity to the infinity, of course, yeah, big number to the power of big number, this is infinity. Or maybe 0 to the infinity, we also prove it that is 0. And yeah, actually 1 to the power of 0, of course, is 1, because any number different than 0 to the power of 0 is 1. That means they are not indeterminate. They are determined right away. How we can, yes, how we can focus, I mean, how we can deal with the power forms. We will change, in order to compute that limit, we will use the logarithmic form or we will use the exponential form. I mean, we may take this form, f of x to the power of g of x. It's not a power form, it's not an exponential form, but we can rewrite. Taking natural log of both sides, because naming this as a function, we may take ln of y, and also ln, natural log of f of x to the power of g of x. And when we have a power, that power can be placed in front of the logarithm, if that's the property. If we have this, we may move it in front. Yeah? And then we did create a product, we can go from there. Or we may, but then we have to remember to take again, take care of this ln of y, because this will be not a y, will be logarithmic. But the same thing, just a different like angle of looking at this logarithmic, we may use the exponential. Yeah? Having a form, again, f of x to the power of g of x, we will rewrite as a e to the power of this number. Because we remember, when I have, let's say, a number a, quantity a, I may rewrite as an exponential form, e to the power of ln and that a. Yeah, that means this is my a, and I did rewrite as a e to the power of ln, and f of x to the g of x is my a. And to simplify even further, using exponential logarithmic properties and exponential, g of x can be placed in front, so we can see in front of the logarithm. I mean, that's how we will operate, and everything is placed in the exponent. Now it's an exponential function, natural exponential function. We may look at that limit in the exponent, and the final answer will be e to the power of that value, if this value exists. Okay, exercise number 1. X to the x, one of the easiest power form. X goes to 0 from the right-hand side, then we have 0 to the power of 0. This is indeterminate form, and let's apply the exponential form. Limit as x goes to 0 from the right-hand side, and now I am rewriting e to the power of ln, x to the power of x. Limit as x goes to 0. That x in the exponent I can place in front of the logarithm. Now everything function exponential e to the the natural exponential function is continuous function, and we can see the entire x formula is placed in the exponent, and we will apply that limit to the exponent, e to the power of that limit. X goes to 0, x to the power of ln of x. And the final answer is e to the power of this number. But we have to take care of this. Let's use maybe different color. We have to evaluate this limit. Let's do it. Limit as x goes to 0, x times ln of x. We end up having a product form. Product, we changing for quotient. We will keep ln of x and 1 over x. Actually product, but I was going on to say indeterminate product. Natural log function at 0 from the right hand side, it's negative infinity. 0 times infinity, that's product indeterminate form. Now we did change to negative infinity. 1 over small number is a big number, in this case positive. Now we have infinity over infinity. We are allowed to use the L'Hopital rule for that form. Let's see. Derivative of ln of x, of course, that h. Derivative of ln of x, 1 over x. Derivative of 1 over x, negative 1 over x squared. And then, after simplifying, 1 over x times negative x squared over 1, because dividing by fraction means multiplying by the reciprocal, we will end up with negative x. X is 0. Final answer, or the final answer of this limit is 0, but we will place that 0 here. E to the power of 0, final answer is 1. Yeah, maybe it's not a surprise, but we do have a strong reason. We justify the answer. Yeah, it's not a guess. 1 is the final answer. Okay, we did everything. Beautiful. Exercise number 2. Limit as x goes to 0 from the right hand side, 1 plus sine of 4x to the power of cotangent. Interesting. Sine at 0 is 0. 1 plus 0 is 1. Oh, blue. Okay. Maybe not. And cotangent at 0. Yes, cotangent at 0 from the right hand side. What it is? It's not 0. We may get the graph. We remember tangent is not defined at tangent of x, at pi over 2, negative pi over 2, and so on. But cotangent is not defined at 0. Yeah? And the graph looks like this. Oh, a little bit too close. That's from the right-hand side. Right? That means this is 0, this is pi, and every that's pi over 2, negative pi over 2, negative pi will be the asymptote. Okay, that means at 0 from the right-hand side, function goes up, and we have positive infinity. But if we don't remember cotangent, if we don't remember the graph, we may also try, I will need extra space, we may try to investigate cotangent of x. We can rewrite as a cosine over sine. And now, as x goes to 0 from the right-hand side, we will have cosine at 0 and sine at 0. Yeah, we're trying to investigate that limit. Cosine at 0, it's 1. No problem. Sine at 0, that's supposed to be plus. I got used to so many indeterminate forms. Sine at 0 is 0. However, it's the positive 0 or negative 0. Function sine of x looks like this. Yeah, this is sine. And at 0 from the right-hand side, function is above. That means it has positive values. 1 over small number, because that 0 represents small number positive, will be big positive. That means that's another way to find out how cotangent behaves at 0 from the right-hand side. Okay. Okay, we just determined that this is indeterminate form. let's see what we will get. Yeah? The answer could be anything. Could be infinity, could be 1, could be even some finite number. We will find out. What we will do, limit as x goes to 0 from the right-hand side, exponential form e to the ln, and I will copy our quantity. Cotangent. Okay, limit as x goes to 0, e, and then cotangent of x can be placed in front of the ln. Okay, and now we're focusing, shall I write this, on the limit of that exponent, because everything is placed in the exponent. We have continuity, we can do this. Limit as x goes to 0, cotangent times ln of 1 plus sine 4x. And then the final answer will be e to the power of that number. So we're looking for this limit, which probably we can see is a product form again. And that answer will be the finite answer, e to the power of the number. Let me add a slide, and I will copy that limit. Insert a blank slide, because I took so many room for the cotangent. Okay, the blue box, cotangent times ln. Shall I use the blue color? Oh, that's not a eraser. Let's use the blue color. Then we know that we're working on the exponent. Cotangent of x times ln of 1 plus sine of 4x. Okay, first of all, let's check, because maybe it is determined right away. Cotangent at 0, we know it's going up, and sine 4 times 0, 0. Sine at 0 is 0. 1 plus 0 is 1. ln at 1 is 0. Okay, that means this will give us still indeterminate product. Product, it's still not ready to use the L'Hopital rule. Let's rewrite as a quotient. What we can do, let's keep ln on the top, because each trigonometric function has nice reciprocals. 1 over cotangent, I can put 1 over cotangent, not cosine, 1 over cotangent, because I decided to flip this, but 1 over cotangent is tangent. And we will like this ratio. It's not it's not complicated. It means dividing by cotangent means multiplying by tangent. Okay, let's do here limit. Let's check what we have. ln at 1 is 0. Cotangent at 0 is tangent at 0 is 0. We have indeterminate form 0 over 0 ready to put h to apply the L'Hopital rule. Okay, derivative of natural log of that quantity 1 plus sine of 4x is 1 over that quantity 4x. Follow the chain rule times derivative of this quantity. Derivative of 1 is 0. Derivative of sine of 4x is cosine of 4x times derivative of 4x, 4. Okay. Derivative of tangent of x is secant square of x. Let's check what we have. We will have 1, sine at 0 is 0. Cosine at 0, because 4 times 0 is 0, is 1 times 4. And then secant at 0 squared, secant at 0 is 1, like cosine, 1. Okay, so you know what we have? We will have 4 and 1. 1 squared is 1. 4. Interesting. That's not the final answer. We have to go back to that other slide, and we will put 4. E to the power of 4. That's the final answer. Interesting, right? 1 to the infinity is giving us this nice finite number involving the number e. Okay, another exercise. Exercise number 3. Okay, 1 plus 1 over x to the power of x goes to infinity. 1 over infinity is small number, that means we have 1 to the infinity. Okay, again, 1 to the infinity. Let's check. Limit as x goes to the infinity, e to the ln, and the quantity 1 plus 1 over x to the power of x. That x can be placed in front. E is missing, e, because this is exponent. E to the power of x times ln of 1 plus over x. Okay, the final answer, oh no, still, e to the power of that limit, because we will apply this limit here. Infinity, x times ln 1 plus 1 over x. The final answer is e to the power of that number. Let's use the same color, blue. We have to focus on this, and this will be the answer. Now I have a rule. Let's figure out what we have. Limit as x goes to infinity, x times ln 1 plus 1 over x. Ln at 1 is 0, and x goes to the infinity. Indeterminate product form. Yeah, we also practicing product forms. Interesting, good. Not ready to apply the L'Hopital rule, we need a quotient. I think again, I will keep ln, and I will flip x, 1 over x. Now we have ln at 0, ln at 1, because that 0 is 0, and 1 over big number is 0. Yes, we good to apply the L'Hopital rule. Let's check. Derivative of logarithmic function, ln of that quantity, is 1 over this quantity times derivative of this quantity. Derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. And denominator has the same derivative as inner function. Nice. We may cancel this out. And as x goes to the infinity, 1 over big number is small, then this is 0, 1 over 1, it's 1. The final answer of the blue limit is 1, but we know that this will go here. Wow, the answer is just E. Okay? And actually, this is the limit. Yeah, we will use this later in calculus too. This is the other way to define the number E. Number E is defined, you might see this before, as a limit 1 plus 1 over x to the power of x. You may try to substitute numbers bigger and bigger instead of x, replace x with like greater and greater values, and you will see this will approach, what is the approximately number E is like 2.72. It will go bigger, but never greater than 2.71. And yeah, we have more decimal values. Okay, nice limit, worth to remember, but we did the entire proof that this limit is equal to E. Okay, I have another one. I have 2 more, exercise 4 and exercise 5. Okay, limit as x goes to 1, 4 minus 3x to the power of 1 over x minus 1. 3 times 1 is 3, minus 4 minus 3, it is 1, okay, and then 1 minus 1 is 0, a little bit more than 0, positive 1 over small number, this will be 1 over small number, is a big number. 1 to the infinity, it is indeterminate form. Okay, let's do the same process. You will be an expert with the power forms, indeterminate power forms. E to the power of, E to the power of ln and the entire quantity. Now limit as x goes to 1. That exponent we may place in front of the logarithm, and now we will focus on the exponent, and this will be E. to the power of limit. And you can even see one, I can create a fraction right away, ln 4 minus 3x over x minus 1, because it's multiplied and x goes to 1. Okay, the final answer is e to the power of that number. But we have to find out. Okay, let's see. Limit as x is approaching 1 from the right hand side, logarithmic function. Okay, 4 minus 3x, x minus 1. 1 ln at 1 is 0, 1 minus 1 is 0. Okay, we are ready to apply the L'Hopital rule. Derivative of the logarithmic function, ln of the quantity 4 minus 3x is 1 over that quantity times derivative of this quantity, it's negative 3. Derivative of the denominator is 1. And what we getting? We will have 1, we can ignore it. 4 minus 3 times negative 3. 1 times negative 3, it is negative 3. Interesting, right? And maybe I can rewrite as a e cube, 1 over e cube. Yeah, also that form, it looks, if we will look closer, it's a little bit of the e definition hidden, but yeah, we got e to the power of 3. I mean negative 3, and 1 over e cube. Okay, let's finalize the session with one more exercise, because I think we didn't really do, this is x, which is infinity, 1 over infinity is 0. Infinity to the 0, we didn't do this one. Maybe we can get 1, maybe infinity, maybe 0, but let's prove it. Yeah, please do not guess. It's definitely power form, indeterminate power form. Let's rewrite as an exponential e to the power of ln x to the power of this, limit as x goes to infinity. That 1 over x I can place in front, and now we may look just at that exponent, and 1 over x times ln of x is ln of x over x. Right? And the final answer is e to the power of that number. Oh, this is nice, quick limit. You probably know the answer. I don't even have to apply. It's limit at infinity. Nice, simple, rational, like ratio of two functions. We may apply the relative rates of growth, logarithmic function versus power function. Of course, power function grows faster. Yeah? And then if the denominator is winning, the answer is 0. I mean, this limit is 0. We don't even have to use the L'Hopital rule. I mean, we can use, you can use, because it's infinity over infinity, we may use h and the L'Hopital rule, but we know that it's 0. E to the power of 0 is 1. But yeah, we did get. It's funny. Big number, infinity, yeah, the 0, we've got 1. But I use, yeah, in order to compute this limit, I use the relative rates of growth. Right? Function x grows faster. It's always above logarithmic. In the denominator winning 0. Okay, we did practice actually the power forms and also the product form. Thank you.